Imagine you have two objects, one at high temperature, so a hot object, say a piece of metal, which we'll represent with this red block, and you also have a cooler piece of metal, so at lower temperature, which we'll represent with this blue block. In this case, there's going to be an exchange of energy between the two objects from the hotter to the cooler one, and we represent that exchange of energy in the form of heat as Q. We would like to be able to quantify or calculate the heat exchanged from an object or a substance, and to do that we use one of two equations. The first shows a relationship between heat exchange and the change in temperature, and also a constant for the particular substance, which is called the heat capacity. So the larger the heat capacity and the larger the change in temperature, the larger amount of heat that must have been exchanged from the substance. Heat capacity is defined as the heat required to raise the temperature of a given amount of substance, so a very defined amount of the substance, by 1 degree Celsius. So how much heat is required to raise the temperature of a given amount of a substance by 1 degree Celsius is called its heat capacity. This is a property that is dependent on the amount of the substance. So in other words, it's an extensive property. For instance, 1 gram of copper will have a smaller heat capacity than 10 grams of copper. Heat capacity has units of joules per degree Celsius. So when we multiply heat capacity times a change in temperature, degrees Celsius, the units of temperature cancel, leaving units of joules, which is the unit that's used for energy, in this case heat. The second equation that's used is dependent on both the mass of the substance given and a constant for that substance called its specific heat. Now, specific heat is different than heat capacity in that it's defined as the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So in other words, specific heat is going to be independent of the mass of the amount of the substance given. So specific heat for copper is the same whether you have 1 gram of copper or 10 grams of copper. In this way, it is an intensive property of that particular substance. To calculate heat exchange using specific heat, we also need to know the amount of substance that's given, in other words, in this case it's mass, and the total change in temperature. The larger the mass of the object, the larger its specific heat, and the larger the temperature change, then the more heat that is exchanged to or from that particular substance. Specific heat has units of joules per gram degree Celsius. So you can see that the mass is sort of a unit within the specific heat. When we multiply mass times specific heat times change in temperature, mass in grams and temperature in degrees Celsius cancel, leaving units of energy, joules, for the heat. Let's do a couple examples. Heat capacity of a metal chair is 1250 joules per degree Celsius. If the chair absorbs 1.5 kilojoules of energy from the sun, how much will its temperature increase. So we have a chair absorbing radiant energy from the sun. Let's say it absorbs 4.5 kilojoules of energy. How much of a temperature change will it undergo? So we're going to use the relationship heat is equal to heat capacity times the total temperature change. We are given heat capacity for the chair. Notice the units, joule per degree Celsius. It's 1250. We know the total amount of heat absorbed, and so we should see an increase in the temperature. Substituting those in, 4,500 joules equal to 1250 joule per degree Celsius times a change in temperature. Rearranging to solve for change in temperature. Joules cancel, and we get temperature changes 3.6 degrees Celsius. So assuming the chair wasn't too hot originally, it's probably still safe to sit on it even after it's been sitting in the sun for a bit. Okay, so this example uses the heat capacity, and you can see how it is defined for a very specific amount of a substance or a very specific object, in this case a chair. Now we'll do an example in which we use the specific heat capacity, or the specific heat of a substance. So example 2, just get that in. How much heat must be supplied from the flame of a Bunsen burner to heat 450 grams of water from 25 degrees Celsius to 100 degrees Celsius? And we are going to assume that the specific heat of water is 4.184 joules per gram degree Celsius. That is a constant worth remembering because you will use it quite often, especially in calorimetry problems. So the specific heat of water, 4.184 joules per gram degree Celsius. So we know that the temperature is going from 25 to 100. We know the amount of water that is present, and we know the specific heat of water is 4.184 joules per gram degree Celsius. So let's do a little drawing. We have a beaker with water. We put it under a Bunsen burner. We know there's 450 grams of water in the beaker, and we are going to heat the water from 25 degrees Celsius up to 100 degrees Celsius. How much heat must have been supplied in order to do that? Well, the heat absorbed by the water is equal to the amount of water times its specific heat times change in temperature. Since we're given 450 grams of water, we can put that in. The specific heat is known, 4.184 joules per gram degree Celsius. And the change in temperature, which is always T final minus T initial, is 100 minus 25 degrees Celsius. Canceling units, we're left with joules, specifically 1.41 times 10 to the 5th joules of energy required to heat the water by that temperature change. And this is 141 kilojoules.